All right, we're going to look at the physics of a back tuck. Here's a pretty standard shot of one. You throw those arms up as high as you can, try to accumulate height, bring the knees in, sight the ground, and then stay tucked so that you get around to make the landing. So we're going to take a little look at what's going on during one of those back tucks. While you're in the air, you're just a projectile, so your center of mass just follows a parabolic path. No matter how much you flail around, your center of mass will just follow that particular path. I'm about 5'4", so that big yellow line is 5 feet. I see that I got my center of mass about 12 inches above where I took off. Let's look at the takeoff. 1, 2, 3, 4, 5, 6 thirtieths of a second, or 0.2 seconds. I was pushing off on the ground. 4, 5, 6, 7 thirtieths of a second, or 0.23 seconds to reach the peak. All right, we're going to see what we can learn from the fact that my center of mass rose by 0.305 meters during the takeoff, from the time that I took off until I reached the peak. During the flight, I'm just simply undergoing constant acceleration due to the force of gravity that acts on me while I'm a projectile, okay? And so what we can do is only while I'm in the air, okay, but we can solve a kinematics problem to learn what my initial vertical velocity was. And so we'll use this kinematic expression, which again is valid for constant acceleration. And what we can do is plug in a final velocity at the peak of 0 meters per second and solve for the initial velocity, which would be the velocity at which I left the ground. And so if we plug in the acceleration due to gravity, negative 9.8 meters per second squared if I choose positive up, and 0.305 meters for my change in position, what we learn is that I allegedly left the ground at 2.44 meters per second. We can actually do an independent check of that launch velocity, given the idea that it took, about a quarter second for me to reach the peak. So let's take a look at that. We can do an independent check of this velocity to see if it's reasonable. Well, that time to peak, which was, close to a quarter second, we can double check that. So we can use this kinematic equation for the trip upward from takeoff to the peak. And again, setting the final velocity to be 0, vertical velocity to be 0 at the peak. We would, in plugging in this alleged initial velocity at 2.44 meters per second, we could solve for the time that it should have taken me to get to the peak. And what we find is that it is indeed about a quarter second. I think it was 0.23 seconds from the frame rate, but it's a little bit of a judgment call about whether I was actually at the peak or not. So it seems quite consistent. Well, given that I took off with a velocity of 2.44 meters per second, we can actually learn how hard I must have pushed on the ground, or therefore how hard the ground must have pushed me upward. And so what we're going to do is now focus on the takeoff itself, so not the flight. Okay. And so, here's your 150-pound physics teacher about to head up into the air. And so there's this force of gravity acting down on me. And what we're going to actually do is use a concept called impulse to find the average net vertical force during the takeoff. Right. Well, so this concept of impulse is just the change in momentum of the object. And so to calculate my change in momentum, I would need my mass times my change in velocity during the takeoff process. And what we can then do is set that equal to the average force times the time of the takeoff process. Also putting in my mass of 68 kilos, my alleged delta V of 2.44 meters per second, and I can set that equal to the average force, upward force, times 0.2 seconds, which was the time in which my feet were in contact with the ground as I was taking off. And we find that the average vertical force then is 830 newtons upward. Right? And by the way, you could have found that same answer using F equals ma if you used the average acceleration upward, like delta V over 0.2 seconds. You should be able to get the same answer. But what does this mean? This is the net upward force is 830 newtons. Well, if the Earth's already pulling me down with 666 newtons, that means that the ground must be pushing me up with 830 newtons more than that. And so during the takeoff, there's this average upward force of 1496 newtons, which is about 337 pounds. Let's take a little look at the initiation of the rotation. So of course we have the force of gravity acting on me, on my center of mass, and the normal force from the ground. Now when I did this particular tuck, I drifted backwards, and so there would have been some force backward from the ground on my feet to help send me that way. So the vector sum of the forces from the ground would kind of point at this diagonally up and to the right direction, but very importantly, not through my center of mass, because if the line of the force were to go through the center of mass, I wouldn't have been able to initiate this rotation. So there's a torque that initiates this rotation in this clockwise direction, because this line of force kind of misses the center of mass to the left, and so that's going to generate a rotation in this direction. So my angular momentum was gained because the line of force provided by the ground does not go through my center of mass here. And if the force were directed toward the center of mass, it would have made no torque and I wouldn't have rotated. Now sometimes people will do a gainer backflip where they'll jump forward, and in that case the friction force would point forward, but then clearly the net force from the ground would not be through the center of mass if it were sort of diagonally up and to the left. Let's take a look at the flight. You can see during this part of the tuck, while I'm all spread out, you can see that I'm not rotating very fast at all. My arms and legs are still spread way out. When I've managed to tuck, you notice that my rate of rotation is much, much faster. So the angular momentum for an object rotating around some axis, which is represented by the symbol L, is equal to what's called the moment of inertia of an object times its angular velocity. So just like linear momentum is linear mass, or mass, I should say, times linear velocity, rotational momentum or angular momentum is rotational mass, or moment of inertia, times rotational velocity, or which is called omega, or angular velocity. Well, so here I am in this untucked state, all on the left, kind of all spread out. And what that means is, since I'm untucked, I have a rather large moment of inertia around the center of mass. And so while I'm in the air, my angular momentum doesn't change, so this product of I and omega needs to be constant. Well, if I have a large I might have a relatively small omega, or a small angular velocity around that point. And so in subsequent frames, I hadn't rotated much when I was in this configuration. On the right, though, I'm more tucked. I've reduced what's called my moment of inertia. So I have a small moment of inertia, and what we saw when we flashed through the film was I had a much larger rate of rotation, or a much larger omega. And again, that simply comes from what's called conservation of angular momentum.